to hear. Yeah.
Say that again?
I was saying that I don't need a lot of time, but if there is some time to just say, hey,
yeah.
It's not stopping now, it will continue.
Yeah, exactly.
Yeah.
Yeah. Do you have any slides?
No, I don't need any. Well, I put my background as a slide, so.
Okay. Well, now I make them. Excellent. Cool. Then we shall hear from you soon.
Yeah, very good. Thank you.
It's hoping that we will be here. Shall we get going then? Right. Good morning, everybody. Thank you for turning up at this early hour. I'm starting straight into the caffeine, that's not good. I'm Stefan Charlotte, the one who wasn't here yesterday. With Business, I had the great pleasure of co-chairing for ECMFA, and indeed I have the great pleasure today to introduce our keynote, which is Andrzej Wąsowski. And I'm slightly worried about the cable on the floor there, if I can sort of over this. Okay, just a little bit of your piece. Which is not the obviously very famous classical piano player, but the professor from the IT University in Copenhagen, who's well known, I think, in this community, so I'm not going to spend too much time introducing him. And he was going to tell us all about why we shouldn't believe in modeling, or maybe we should, and how he got there and back again. And I'll hand straight over to you.
Thank you. Thank you for coming last day. I won't be having anything serious to say. So just to tone down your expectations. It's Friday, it's July. In my mind, like everybody in Denmark, I was on vacation. This doesn't make any sense. So I decided to go for a more, not over a technically heavy talk where I'll be showing equations and whatnot, but more for a lightweight mode to maybe get you into thinking about modeling and about interesting problems, and maybe, I don't expect you'll have questions, but maybe we can have some discussion. Yeah. So I was talking about with title slide I should use, and I thought this is more appropriate because we should imagine it's summer, we are on a boat, we put our legs high up, and let's talk about modeling. Let's not be serious. I will mention some work, but sort of mostly as a sort of fertilizer on which I grow my leaves doodling, but using some thoughts that appeared during doing an empirical study with some of these authors. So I should credit the presents by Thorsten and Einar from Oslo, Chalmers in Gothenburg and Bochum. And I'll be also using some elements from my PhD students, Mahia Mohamed Kashani and Laura Mai. So now justice has been done. So I made this silly title because at some point they asked me for a title. So this title sounds good. I have to figure out some story for it, which is very much a bit hard with these titles. I guess I promised to talk about my disillusions first, how I lost modeling. So I'll start with it, but probably I won't dwell on this too long. Sorry for disappointment. In about 2016, I think, I was giving an important lecture in Copenhagen for my faculty about software engineering research. And I thought to start with some successes of software engineering research. So I'm reusing shamelessly reusing the slide, which is 7 years old or something like that, right? And so this is empirical material, right? Slide archaeology. I wondered, how am I going to talk to researchers in my faculty about what is software engineering research and what is our big successes? So let's see what I have shown. So I have shown a successful launch of an Ariane rocket. because actually that one has more than 100 successful launches, and people typically misrepresent what the Ariane program is an example of software bug, but it's actually a very successful project which never suffered any new software problems again. And it's a huge, we should be proud of it. People work with it, have done a very good job. But then I also shown, this is maybe not very informative, it's in Copenhagen, everybody could recognize it. It's a display in Copenhagen Metro, which is an autonomous train. And all of us were getting to that lecture, using this metro without thinking that it would kill us. All right? We take it for granted that this software works. And similarly, I continued. This is not a lecture about it's probably plugged in here. So similarly, I was showing examples of other systems, and I'll flash forward, right? Because that's not important. Fire safety systems that we have in all the buildings, traffic control systems, cars, not autonomous cars, non-autonomous cars are huge software machines, and any problem with this software could potentially kill us. We trusted without thinking, we drive and drink coffee while driving, and I think this software is working, right? This is a huge success. And now we're getting autonomous cars, which are even a lower fatality rate than the non-autonomous cars, right? And we are flying big airliners that are basically software-controlled machines with a little bit of human supervision, right? And we don't worry. So that was my story about success of software engineering 7 years ago. Where is modeling? Where is testing? Where is program analysis? Where is verification? Basically, this slide, it could also be sort of psychoanalyzed as an admission that what we are doing doesn't matter. I mean, I'm trying to overdraw. I can see Martin getting a grumpy. But maybe what matters is somewhere else. And maybe we kind of got detached with reality in a way. This is where the action is, the real system engineering, not building model-driven engineering tools. Okay, this is trying to psychoanalyze me 7 years ago, but something must have happened in my research life, because ever since I have not written a proposal about modeling. I have written research proposals about AI, data science, privacy, robotics, autonomy, and these are the kind of projects I've been running. I have not written a proposal about designing a new meta model. So something has happened. So I probably lost my place in some sense. Now, that's probably what I can say about it. I'd like to take a different take on the issue and maybe not talk about my personal life crisis as a researcher, but more about the funding landscape, how the research funding agencies look. So I made a small exercise. Look at this. I made a small exercise, and I looked in the Horizon Europe Digital Industry and Space chapter of the work program, which is probably the one that many of you study carefully, finding some point where I can squeeze in a model. And I looked at some examples of what is being funded, and I tried to make them presentative. Yeah, because I cannot post 3 pages of topics, so I selected some. So efficient and trustworthy AI, making the best of the data. That's one thing you can write proposals on. Actually, you could in 2023. Intelligent data acquisition and analysis of materials, smart sensors, integration of data lifecycle architectures and standards for complex. That one, I don't even know what it means, honestly. It's complete gibberish. I hope there's nobody from European Commission here. Yeah. Okay, so novel paradigms and approaches towards AI-driven autonomous robots. It's pretty clear where the Commission thinks the action is. Right? It doesn't seem to be in SysML or IADL. Right? And maybe this hurts a little bit, but that's the picture when you're reading the work program. Right? Good news. I read a little bit further down the page for 2024, and there was fundamentals of software engineering. So I suppose there are people who were writing for that already. Look to one, please. So you probably all should now take note, and I can give you the call number. The call number is here. But there's two things you should be aware for. There is budget for 2 projects to be funded. Okay. So probably going to be competing a bit hard against each other. Maybe 2.5. So write smaller projects, maybe they can fund 3. Okay. And then, well, looking into the scope of the proposals of the call. So this is the details. If you open the large document and find the right page, you might find yourself a little disappointed as well. So it's about methods and mechanisms and tools that allow smart, intelligent system specification. Okay, at least the word specification is there, right? But it's quite likely that this call will attract a lot of AI proposals. And it's quite likely this will be very strong research groups and this will be very well written proposals. So just warning you. And if you continue reading, there's things that sound familiar: complex requirements, designed by contract, semi-automatic creation of precondition, postcondition. Okay, semi-automatic creation of precondition sounds like large language models are going to be funded in this call. It's not likely that we have, let's say frankly, we should be trying, but it's not likely that a lot of research out of this community is going to be funded in this community. It's not likely. So, going a little look here, and we thank European Commission for killing model-driven engineering research, right? Well, maybe we shouldn't say it so. We should be thankful that for many years, the European Commission has been a lifeline of this community in many ways, because it has funded. But the picture now looks a little tired, at least on this first part of the talk. So maybe it's not just me who is in life crisis regarding model-driven engineering. So now I want to do example here. Start playing this, and hopefully this stabilizes with Zoom, and I'll tell you a little bit about it while it's playing. So let's forget funding and funding politics, and let's talk vocabulary. So what is a model? So we used to believe that models are things that are built by you or me or an engineer or a scientist, so someone who understood some domain very well, right? And he captured the knowledge. They captured the knowledge and express that knowledge in a model that can be reused for something, control, monitoring, whatever it be, some scientific theory. But today, if you want to Google and start to Google from models, it's not what you're getting. Models are things that are basically extracted from data. And so they don't capture knowledge. There are some kind of fractions of data. Well, this happens on so many levels, and this is just one example. So I start maybe with recalling that in this community, in ECMFA, in models, in ICSI, there will be tons of papers about using models to generate test cases for this. So using models in Alloy, structural models, eCore models for generating instances of languages to test tool chains, I don't know, generating configurations from feature models to test software in different configurations, generating traces from timed automata to test the runtime behavior and monitor things. This has been a pattern, right? We have a model, we can generate test data out of it, and we can feed that test data into the system. The model acts as a specification, right? And then we can see whether the system behaves well, or sometimes it acts as a specification. So this was a pattern. So this video here is an example from a PhD student, Laura. So what first I should tell you what happens. It's a video. It's a bit dark, but I don't think I can help. So I'll maybe try to be very descriptive instead. It's a video shown taken by an underwater robot, which performs a simple operation, which is finding a docking station and then docking into that station by Copenhagen here. What's going on? So it's in the wrong place now, but these QR codes, it help it to realize where it is, so that less intelligence is necessary. But this, okay, so it's going down because it knows that it should be somewhere down. And this QR code here is the important one that sort of says, okay, here is where you talk, right? And then it has to slowly enter these creepers that you see on the side that will talk it. So this robot is using vision to do that. So it's using vision for multiple things to track its motion. I mean, you can use accelerometer to track motion, but it's a good source of motion information, but not completely sufficient, right? It's not precise. So you can also use vision, and vision-based localization and mapping is very common these days. So you can also use GPS, but not underwater. It's out of question. So this robot has a component that is using vision to help the navigator to perform this docking operation. And this component has a bunch of complicated phases. It has to track points on the image how they move. It has to transform the image into a 3D thing. It has to do segmentation and pose estimation and object detection. So it's a bunch of phases that are complicated machine learning elements that you have to test for this too. So you need test data, right? And the truth is, this is actually the test data. So this video is synthesized. It's not a real video. This robot has not followed this trajectory. It's synthesized from a machine learning model that basically learned the 3D space of that pool where the testing is taking place. It has used one video or two videos to learn about the space, and it was able to generate more videos, right? Because generating these videos is expensive. It's actually been made in Bremen. The original video was taken in Bremen, and well, there is a testing facility in the FKI in Bremen. It's an expensive thing for a research institute, right? Because you need to have a hall with a swimming pool, robot pool, right? With cranes and technicians. So it's a larger budget operation to make these videos. You would like to have technology to make more of them cheap, right? So this video has been synthesized by a machine learning model, which by analyzing some trajectories is able to create new trajectories and new videos. This is a very new and exciting technology, but that's actually not the topic of my talk here. And what I want to say, notice what happened. People start to call different things models. We're still using them for the same things as before. We use them to generate new test data. But what has happened, the modelers have disappeared, which is slightly disheartening, isn't it? We are not there in the picture anymore. There is data, there is robots, video taking, and a big machinery to train a new model to generate more data. And we call it a model. Is it said? Well, I don't know. Just food for thought. Just food for thought. Okay. So I'd like to concentrate my disillusions or worries or discussion points in these three points here, which I will upfront call fallacies, so no suspense. It's Friday, I cannot give you stress, right? Stress, double home disillusion about modeling. But let's, for a moment, for the sake of discussion, assume that nobody does modeling anymore. People just do AI and learning. It's sometimes the picture you can get. Right? ECMFA program committee, that's what people doing. It's just the large language models. Not modeling, that's the same thing. Okay. And then we do not need to teach modeling anymore because models are just arising from data by learning, right? And the point I already mentioned, modeling research is not fun. So I'll be mostly talking about the first one because it's easy and it's not particularly deep, but we'll also touch on the second and third, and maybe we can have a small discussion in the end where this is all going. And then we go to Stefan, and he'll tell me some nice ideas in the ending as well. Okay, so another video, not this one, please. This one. Maybe I should be conscious and stop this. So this is a video taken by another of my students. It's maybe not very important, but it's actually taken in the same project. It's a Marie Curie network on the reliable underwater robotics. And this is another testing before, sort of cross-cutting a few PhD projects here. So this is not a docking operation, and we're not talking about perception and video pipelines. But we are talking about a robot that needs to perform inspection, and it performs a well-specified maneuver. It has to follow this is called helical trajectory. So go down. At some point, this is a little choppy, but okay, it's too short, but we'll start again. There is this installation element. You can see it here in the simulator. this tower here, right? And this robot basically has to take, I think it's this one, it has to take a few rounds about it to take pictures. So it's a pretty fine task. It just has to realize this trajectory, right? So how do we test such a system? Well, this is a much more standard system than the video-based talking that we talked about, right? In principle, we know exactly the equations that describe the trajectory. We know the equations that describe the dynamics of this atom. And we just need to build a model, and we can do runtime monitoring to test whether this algorithm works, right? So the good news is that, the first video I was showing is maybe a little extreme because it talks about the perception system for which we don't really have good specifications and good models. But there is tons of other things in the robotics and autonomous systems that actually do require models, and it doesn't make sense to test this using machine learning. It's much better to take the control theories, write down the equations and see whether this follows the right thing. Yep. So I think modeling is still there, right? And we are still in the game, and forever, I would say, because it simply doesn't make sense to replace with our very good understood control-based models with crappy abstractions extracted from some random rounds. It's incomparable. Okay. So that's the sort of example I could pull from our research, which tells me that we're going to see use still of both kinds of models that are learned and models that are built. This depends for what we will be and for what we'll be using them. I would like to talk about how I'm going to build this argument that people do reasoning, people do modeling. Well, basically, in 2016, I gave the talk and I started to write proposals about other things, and I started to work with other people in statistics, robotics, wherever, and AI. And, it's 2023, and then I didn't stop modeling, and I see models everywhere, right? So maybe what I'm going to do is I'm going to show you some examples of models I'm seeing, not too many, because yeah. So one example I can show is the language of behavior trees, which is a new rise in robotics language. I should have known, but I should have prepared that. Probably 10 plus years old now. Originally invented for computer games, right? So for programming these NPC characters and all sorts of autonomous things that happen in the game, and you will behave in some animated fashion that looks remotely intelligent. Yeah. And it was super popular. And then robotics people figured out, wait, this is similar. What we are doing is just our agents are physical. Right? So they started to experiment with it, and it kind of became popular. So it's sort of the buzzword in robotics that replaces state machines to state diagrams, these kind of connections. And maybe some of you don't know about it, so it's an opportunity to learn a bit about it as a sidebar. What do we see here is a model. I have taken some notes in which order I should present it so that it is understandable. We should start reading this at the bottom. So actually, I should say, because we are in Leicester, and I have written here that the model has been developed by something called Knowledge Media Institute at Open University, which I believe is just a short hop from here. But that's accidental. This was the random model I picked up from a data repository, secondly from Keynote. It's not made in an MDE group, right? It's an AI robot. And this comes from a case study of a safety robot inspector project. It's a mobile robot that was doing some kind of similar thing to what we were doing underwater, but on the ground, going places and checking out things. Yep. In the bottom, we have sort of a sequential program. We see it because it's a sequence. It's a sequence in this one. So three things happen in the sequence. There's some kind of stack of waypoints. The robot pops a waypoint, looks at the waypoint, okay, asks the base. The move base is a component in the robot operating system that basically navigates to the waypoint. So it's a sophisticated, complicated action to find the paths and move the robot to the waypoint. And once this has happened, the robot performs some exploration, which is another sophisticated action, which is under specified. It's implemented probably in part of the machines. And this is all put in sequence. Now, the semantics of behavior trees has a maybe somewhat unusual combination of data flow and control flow, in the sense that all these nodes also behave a little bit as it's sequencing, so it's controlled, right? But it behaves also a little bit like a data flow. Each node returns a success or failure status, yep, and propagates it out. So if a pop waypoint thing fails, this means that we have explored all the waypoints. The list of waypoints is now empty. So popping fails, and basically the semantics of sequences is that if an element fails, then the sequence fails. So this is propagated upwards as well. And then there is an inverter node that turns a failure into a success. That's a very useful node in life. So then it says, oh, I succeeded. And basically this node above, which is basically a retry loop that says try 10 times until successful. So this is a loop. And then on top, we also have a while true loop. Okay, forever do this thing, collect waypoints, and then try 10 times to explore this waypoints. Right? So that's the semantics of this model. We could draw a state chart of this behavior, is no problem. There's nothing revolutionary from expressiveness point of view going on here, in my opinion, as language design. I have written on the slides, this is a table from our study of the practical use of behavioral languages that summarizes what the language can, but I think I will just move on in the interest of time. But maybe just to mention that parallelism and concurrency are sort of supported in this language as well. It's sort of proper reactive programming language. And maybe one thing that is also interesting to mention is that the semantics actually, at least I believe so, depends on the implementation, time triggered, not event triggered. So the model is basically queried every time tick. All the nodes are executed, and that's how it advances, not when some events. You could draw a state chart of it, and I did, but I will not discuss it because that's boring. That's what we were doing 20 years ago. Today is much more interesting to why we are not doing this. What we did with Torsten and his students and with Ayla is once we thought that this language is popping up, we tried to understand how people use it in robotics, and we wrote papers about it, very long DSC paper that has just been accepted. If you're interested, I'll get you there. But maybe just sort of some fun facts here. So it seems that out of these studies, we know that the behavior trees the use of behavior trees in robotics is growing pretty fast. I mean, we were able 3 years ago to find 7 implementations of behavior tree libraries. So it's independent language. The language is not standardized. So 7 different implementations of different dialects of behavior trees. Arguably, only 2 of them were reasonably alive. And David, who is one of the authors, is making a new one now. So some turmoil is still happening. Then we went to GitHub and we tried to find how many projects use these language implementations, right? And we found 3-4 years ago, almost 300 projects that use behavior trees easily. They're all robotics projects. I mean, they're also gaming projects. So we have to separate them. We were interested in robotics. And this graph here shows, tries to compare popularity of state machine models in robotics versus behavior tree models in robotics as it was in, I believe, 2021. FlexB and SMAG are implementations of state machines that robotics people use. And PyTrees, ROS, and behavior tree CPP and PyTrees are implementations of behavior trees. And this is, since these state machine libraries are much older, there is way more projects that use them. It's about 3-4 times more. They're around for many years. Yeah? But what we looked at is number of active projects in every year since 2011. GitHub, so if the project had any commits. And you can see that the line for SMAG, so with state machines, has essentially flattened. And the line for FlexB, which is the red one here, has also flattened. Whereas the 3 lines for behavior trees are much more steep. And if you add them together, they actually more than these 2 lines. distinctions, right? So there's more active, already 3-4 years ago, there was more active behavior tree-based projects than state machine-based projects. So this judging by will keep happening. Now, some other anecdotal information, you go to IROS, there is likely going to be, IROS is a flagship robotics conference, there's likely going to be behavior tree workshop, people discussing how we can benefit from these models. The ROS2, which is the main robotics programming framework on the planet, it's used by hundreds of thousands of people because all robotics departments teach all students using it. It's using behavior trees to customize the navigation stack. So the thing that moves and finds paths and moves robots, you can customize how it does it and how it reacts to various disturbances by providing the right behavior tree. And anecdotally, when I talk to companies in robotics, I have no idea why, but they all ask me, why wouldn't we use behavior trees? Use a transition system, so very expressive. But the companies seem to be excited. I don't know what's the reason for this, but now you're also excited. What it tells me is that, in 2023, people use modeling a lot in robotics. The same people who are also using machine learning now, because they do in the same projects. And this has not killed modeling by no means. Okay, so it's time for a commercial break. So together with Torsten, I have recently finished writing a textbook for designing domain-specific languages for model-driven engineering and automation software development. So this is a shameless plug for the book. This is a teaching book. It's a textbook, and I also promised to talk about teaching a little bit here and there. So I'll try. It's a book that aims not for you, not for researchers that are experts and PhD students. It aims at bachelor students and master students who want to learn to design languages. Well, you should give it a look because maybe you want to show it to students, right? That's my message, the subliminal message. It's out now. The book is very hands-on. It has a large code repository. It mixes modeling and programming language traditions. So I think that one mistake we did as a modeling community in the past is that we defined modeling as being UML or modeling as being SysML or modeling as being Igor. None of these things is true, right? You can do modeling in Haskell if you want. And that book tries to combine make a uniform perspective that doesn't make these additional distinctions. So it does functional programming, object-oriented programming, it does Igor, and it has tons of examples from various domains, which some of them you can see here. And it does not depend on Eclipse IDE. Although it does use Igor, for example. And importantly, it also, I think, tries to professionalize language development. So testing and quality assurance and requirements are discussed in every chapter, in every phase of language development. Right? So it's really a book which is supposed to teach you how to engineer languages. And it is sort of academic. It's not an engineering history. I think it's a perfect textbook for your next course. But why I'm talking about it? Well, because also in this book, we have one of the running examples, which we call .robot, is a reactive programming language, which is not unlike behavior trees. Actually, behavior trees are mentioned here and there in the book, of course, because the same set of authors is, but they don't play a major role. But what I think is important is the paradigm. How do we design and implement such languages? To implement behavior trees, you have to know how to integrate it with ROS, which is a very complicated real-time concurrent framework. And there is no way going around that. And that's why the teaching book has to do the same. So we have a tiny hierarchical behavioral event-driven language, which is a bit like textual state charts. And we use it as a running example to interpret it against the robot. And then actually, but this is just a side note, maybe there's someone who cares more about programming language here. We do this cool thing where we show how to take an interpreter and how to turn it into a code generator using binding time analysis. But it's not very important, but what is important, I think, for the whole story here is that if reactive programming languages or modeling languages remain relevant, then we have to teach how to build them and how to use them. And that book also does. It's one of the examples. Okay, so nobody does modeling. Maybe that's a fallacy in the end, or maybe it's just reactive languages. Especially for Alex, I have one slide here. It's not only reactive modeling languages, there are other things. Actually, if you open a robotics project, which is relatively complicated, there'll be tons of models there for various things. There'll be tons. I bet at least 10. At least 10 in a small student project. So this is another example is hardware description languages. If you want to implement a relatively generic robotics framework, you have to somehow tell the framework what is the shape and nature of this robot, right? Which parts it has and how they move. And that is done by robot description languages or description languages. And the popular one, which exists, I know that here since 2011 at least, but that's just because I lost patience searching whether it's older. But in 2011, I had evidence that the product existed, so it's pretty old. It's an XML-based language called Universal Robot Description Form, URD. And I actually added, you can probably believe this XML means something. It's easier to explain what it captures in the figure. Well, it basically describes what is the base of the robot and two kinds of parts, things that are called links, the blue things here, and things that are called joints, the red things here. So links are things that are stiff, they don't move, and joints are things that move. Yeah? And for joints, you can describe what kind of move it is. It's bending or is it rotating, what kind of degrees of freedom, right? And the system uses this to know, for example, if the base moves, how this affects the position of this point. So the entire geometry of the robot, how the robot when it evolves. Or when I bend this guy, how the whole shape will change. Right? And often it's accompanied with other models that are provided with drivers, which are meshes to visualize this thing. So this is a visualization of this thing that has been done in a digital twin, right? Called ARGIS problem. So these URDF models often come with extra models which says how to render this, so that you can have a digital twin for free. So it's not just reactive programming. There are other applications. There's tons of models for knowledge of the robot, but also for simple software engineering things like how to launch the robot, how to screw the robot together. And good, I have to hurry up. So everybody seems to be doing modeling because it's not only the robotics people. So let's switch domain for a moment. Let's talk about statisticians and data scientists. The people who are kind of danger because they deal with data and they extract information from data and maybe they make us irrelevant. But they're doing this by building models, which is distracting or disturbing, right? So I want to talk about probabilistic programming models. It's another domain in which I have. Okay, this is a model in a Jupyter notebook, but I want a more concise implementation. So I moved it representation. I moved it to an editor so that we can have 8 lines close to each other and talk about it quickly. So what is this model? It captures a regression problem. The key line is here, the line which starts with y. It tries to say, okay, let's try to predict someone's weight from someone's height. Let's try to predict some. So x is weight. No, x is height, y is weight, and we are trying to predict height from weight. And we assume, we make an assumption in the model that that relation will be linear. Right? So we're going to multiply someone's height by some constant, the average, weight of a centimeter of a person. You don't know, right? And we're going to add some constant, some basic weight of a person. Right? So this is an assumption in the model that this is going to be a linear relationship. And then we say, okay, we don't know. So this line y here, it's kind of hidden here. But maybe I'll go back to the representation in language in a moment. What we're going to say, we're going to make this relationship probabilistic. So we'll say, okay, we don't know what is beta 1 and beta 0. So we will say beta 0 and beta 1 are such as some uniformly distributed variables. Our prior knowledge about them is pretty weak. Yeah, we don't make any assumptions. And then we are also going to say, okay, it's not really so deterministic that if you have x centimeters height, and if you multiply it by beta 1, beta 0, this gives you your weight. Yeah, there has to be some noise. We are all different. Someone's skinny and someone's less skinny, right? So we're going to admit normal noise about these results. So basically, we're saying this equation gives you a mean of people's weight for this height. Yeah? And then we're going to advise that the noise will be controlled by a standard deviation sigma, which will also say something distributed on the scale from 0 to 30. We don't know what it is. So this is the model. And this is the model written in the programming language. We have beta 0, beta 1. This is sigma. They are just uniform distributions. This is Python, a framework called Python. And this is the normal likelihood, the last one. So this is the equation that the mean, we expect the mean weight to be that, and with this standardization deviation. And then the important part is here, which I have removed a few lines on the top. We'll say we're going to inform this model from a data set. This Y is a set of 500 samples of weight, height pairs for humans, right? And we're going to run an inference algorithm on this, which will infer this relationship. So these numbers, beta 0, beta 1, sigma, out of this data. I want to spare all. I'm trying to avoid not going into probability details, right? I wanted to talk about enough about this model so that you have some idea of what it represents. So this is how the model is programmed in reality. This is the visualization that you can extract from the library. It's essentially a syntax tree of this bias graph that this is constructing. So we have beta 0, beta 1, sigma, and this normal distribution depends on them, and we have 500 samples that this is going to be informed from. Okay. So this is the model construction code. This is the invocation of the interpreter semantics. So this is not the model anymore. And the interpreter here is complicated. It's non-trivial. You know, it's 6 statistics books. It's a field that dates back to 40s. It's 8 years of research. 8 years of research in this field. It's not something that we can generically come up with. This is working, right? But it's still a modeling language. And the outcome of this model, once you have interpreted it as graphs like this, right? So these are possible regression lines. You get more than one because this is a Bayesian model. So you actually get a distribution of possible regressions. Say, okay, the most likely is probably here in the middle, if you wish one. And the crosses are the data sets. Or you can look at possible values of beta 1. It seems that the most likely value of beta 1 is here at 30. There are other likely values, and probably down in the details, it's very unlikely that this beta is so. Okay, so this is the kind of language. I'd like to look at this as a modeling language for a moment. Yeah, so forget statistics and stuff. So it is a DSL, it's very obvious. It's a textual language, right? It's written in text. It's an internal DSL implemented in Python. For better or worse, I don't think it's particularly well better hacks one could do from language design perspective. There's amazing better, but that's a different story. Okay. The programmer using this modeling language has to do these factory calls, right? This is, I don't know, when I ask my students to do it with eCore, they suffer a lot. This seems super difficult, but these statisticians do it, construct models by aggregating syntax objects, just, it doesn't seem to bother them. I don't know. But this is what it is, right? These are calls to factory objects of model elements. And so is this. What is mainly interesting about this modeling language is that, well, it's developed without any modeling framework, any transformation framework, or any modeling person. It's done by people who do statistics, not us. I don't know whether it's a problem. I think at this point of the talk, I would like to make the point that it's very cool that it's other people, not us, doing modeling. This is a success. Okay, and the last one, commercial break for the DSL book, the same book I talked about. In this book, we also have a small example of a probabilistic programming language, and we implemented both using eCore and not using eCore, and we used to interpret and code generate and also create graphs like that. So we're also playing with these kind of models, not only automata. Okay. So nobody does modeling I'm less and less sure. Maybe machine learning people are not doing modeling. And this is first of all, I'm just a reviewer for European Commission in one of the AI calls. I have to say that there was a lot of modeling ideas in these proposals. Not allowed to talk about details, but there is. I think AI people are doing modeling today. They're not talking to us. Maybe we should be talking to them. This is an example of a project. This is very popular among AI community right now, at least in Europe, AutoML, which I would call, but 15 years ago, we used to do this kind of research, what we call design space exploration. We would build models under specified models of designs, and then we would write optimizers to those and Pareto prompts. Okay, this design is better than that design. So AutoML is that for machine learning. It learns hyperparameters and architectures for models so that they perform better. So it's a bit like the story I said with testing. Well, we can do the same thing. It's just models are different. Right? The whole idea of engineering and design exploration is exactly the same. They're just using machine learning. So I would say modeling ideas, or at least ideas we came up with, they also came to machine learning. So I would say, let's fix the fallacy. I would say it's not like nobody does modeling. Everybody does modeling. You're maybe not looking well enough. They also all do learning and AI, but this doesn't seem to be action. Now I have about 15 minutes left, and I have two shorter points to make. So let's try to hit the we don't need to teach modeling anymore problem. Okay. Well, if everybody does modeling, these statisticians and roboticists and control people and mechatronics people do modeling, then maybe it would be good that they know something about it, right? I'd say that's the short version of second. If everybody does modeling, it follows by deduction that everybody should be taught modeling. Otherwise, they're crappy modelers. But some concrete examples. I already talked about it. I showed PyMC, and I was in the probabilistic model. I said we are basically constructing abstract syntax trees. This language doesn't have concrete syntax. Yeah. This is the same example in behavior tree world from a library called PyTrees. A piece of program. Unfortunately, I didn't write down from where I took it. Sorry, not a very good credit. But this person here programming is basically building a behavior tree of saying, oh, let's take the root object and add a child, and then let's add more children here, and let's create a selector node, and let's create a running node, and let's set some priorities. This is a very messy code that builds this model. For better or worse, what my students find extremely difficult to program at this level, but these people do it. There's lots of projects that use PyTrees. The other library that is popular, behavior tree CPP, is slightly better because it has this graphical tool I was showing the screenshot. Yeah. So programming with abstract syntax trees, it looks like it requires language-oriented programming skills, and people would be way more efficient if they tried this at university. And this is something we teach, right, in our classes. Also, another benefit is that if these people are taught modeling and language-oriented programming, maybe they will actually build languages that are not so hard to use as these PyTrees. So it's both helping the users of the languages, but also the generation of designers that can do much better languages. And another thing that I think is important for students is when I look at this project, it's slightly visible in this PyMC, but I don't want to show you hundreds of lines of code, is that when you look at these internal DSL models, they often completely mix the model construction code with other logics. And this is a pain to read as a software engineer, right? Because you have a well-defined model that says this is the high-level structure of the behavior. Oh, let's also consult this and that and send a message somewhere in the meantime while we're building this model, right? I think this basic understanding of software architecture, what is a model and what is the concern A and concern B, this is something we teach in modeling courses, and the people will benefit. So, I think you should take care of your undergrad students. master students, maybe not also yours, maybe some of those in the mechanics department next door and in the statistics departments next door, right? I don't know, AI research lab. And give them a favor by making sure these modeling courses exist and they are selected, and you argue why. I am particularly very concerned with my own university, where I look at the data science program, which attracts brilliant students. And I love to work with these students, and they are so effective and they build things so fast. They build things so badly, because the data science program does not include substantial amount of modeling, which also means that they are very good in handling data that's in a CSV file. But if we have a complicated data model, like an electronic patient journal, they're helpless. And this one has hundreds of pages and non-synchronized events, and you have to reason about it. And for that, you basically need to know class diagramming very well. It's the first step. So I think data science, you probably see it in most of your universities where data science is creeping in computer science programs. It should not mean that we stop teaching modeling and architecture, because that's equally important. So let's fix the fallacy. Teaching modeling is more important than ever when everybody does modeling. Right? We should be teaching modeling to everybody. It should be fixed. The last point, I think we well on that. Let's look a bit into research funding. I know Martin was making faces, and I kind of guess why. Because, of course, in most of these topics I have listed here, there is modeling research possible. And most of us have figured that out because we are partners in projects and doing different things, right? So, but just to not be completely speculative, when you look into this, what kind of projects are funded in this one, I think this is now known. These projects that there's a lot of pipeline modeling, data pipeline modeling, and design space exploration, but also collecting knowledge. So a lot of these projects use modeling in terms of ontologies. So they capture prior experiences with models and in ontologies, so that when you build a new data pipeline, you can have a look at what happened before, what worked and what didn't. Right? So this kind of modeling research happens there. When I opened this one, I think it was intelligent data acquisition analysis of materials. This is essentially, it sounds kind of scary, but when you open the scope, it's actually a digital twin project. It's a digital twin project for physical materials. Super interesting. And I think there is space for some people here to work on digital twins. Now, this integration of data life cycle, I was trying to understand what it means, so I did open the scope. I still don't know what it means, but it smells a bit like projects that the European Commission was funding about 15 years ago about model bus and integrating artifacts and stuff. I never particularly believed in them, but they were useful for source of funding for PhD students. And this seems to be the same kind of idea for data. Now it's replaced in modeling terms. So probably we would find some space for us there. I was reviewer on this last one. I can't talk about the details then, but I can tell you there was a lot of, and again, mostly pipelines and knowledge of, about these pipelines. But what is striking, that I can also, I think, tell you, is that there weren't modeling people. Maybe I have seen one name in the pile of discussions that recognized. Everything else was AI people doing that. So there is also a risk that if we don't engage with these communities, they will reconstruct the universe for themselves. This to a large extent already happens in robotics. There is a model-driven engineering community in robotics. It's a large project called Prognosis and several other projects in Europe a few years back. These guys, they're doing a lot of modeling and meta-modeling and building robots. CA was partnerizing about Papyrus for Robotics yesterday. Speakers are here. Papyrus for Robotics was also developed partly in this project. Also in other projects, but these people don't come to models to ECMFA. They have their own workshops in Iros like that, and they never talk to us. I think that's kind of sad. So some ideas for funding are there, and one way how to kind of be a bit proactive to do that is to talk to Stefan. because Stefan is doing some amazing work, not only in theater, on stage, but also in making people write proposals around the MDE.NET. And I think we had a few calls that I found very interesting, because everybody knows what I'm talking about. This is obvious things. These are obvious things. But what happens is to have Stefan who tells us, okay, now you write for this code and you write for this code. And this way we get modeling fun. And that is super useful. Thank you. And I'm pretty sure if you don't know about MDE.NET and the network of networks meetings, you probably can accommodate. That's not to be possible. Because for him, more than Mary, it seems. Okay, instead of talking how to write these proposals, you talked to Stefan about it. I thought I'll finish with listing some research problems. But I think I do something that are interesting. Not necessarily for you, but I think I would be interested with them. But maybe I don't have a block on them. Feel free to pick them up. I'll start with an observation from the paper again about behavior tree. That we looked at this and we conjectured that the identified simple reuse mechanisms in this language are sufficient for what robotics is a conjecture. We're not really sure. What is really, to psychoanalyze these sentences, is we're saying we are not really certain whether the designer of the language has done proper domain analysis to understand what is needed. That's how you can translate this language. Trying to be polite, I think it might be sufficient. But domain analysis, this is a cover of a new book by Marcus Luther, is one of our secret powers. Right? I use the cover not because I think the book is so great, but the title is great. Yeah. What is domain analysis is how to understand almost anything. The title is great. And this is what we can help with, right? We cannot possibly tell robotics people how a robot works, but we have a systematic process how to capture this knowledge. So this is how we can enter, well, I called it tentatively the action kind of research, where you can say, okay, you can work with your domain expert as a coach of the process to come up that your artifacts are better quality. And a better execution process is important when writing European proposals. It's a kind of a process-oriented argument why this execution is good. But there is also a lot of people here that build tools and tech, and I would tell you, okay, there is a lot of work to be done by moving the technology we have to spaces where people are, right? Not to these empty spaces where we are. So move it to R, to Julia, to Python, wherever your users are, to ROS. Yeah. There's some interest. When I writing the book, I was kind of amazed that some of these things pop up, like NFM, the implementation of eCore.net, or PyCore, implementation of eCore in Python. These are very loaded things that allow a lot of stuff. Then I think I kind of hinted by some comments here and there that some empirical research about these modeling languages that people build outside modeling community would be very useful, because they come up with these some half-ass arguments we were using 20 years ago. Behavior trees are more reusable or more evolvable. How do you know that? I mean, these are claims that I hear all the time, but I don't believe them. I discard them because I haven't seen any evidence. Right? Has anybody ever proven that this model is more evolvable than a state chart? I have not seen them. Okay? So these kind of questions for various languages created by expert users are very interesting, and I think this is something we talk about and we know about, how to evaluate and study this. And finally, maybe a point I'll zoom in for a minute. I think it was also transpiring through the talk that models and data are, they're not going to disappear. It's not like one or the other will win. Most likely we need to find a way to combine. Right? And what happens, we really have to combine a lot of code, because nobody talks about code, but actually in the system there is a lot of code all the time, right? And the data or machine learning components and the models, right? So we have to work on things, on ways to combine that. And if I need a slogan for this, I think I wrote it somewhere here. Did I? Yeah. Model what you know and learn what you don't know. That would be the ideal situation, right? Because modeling is what we believe, captures what we know, and there is no point to discover Newtonian physics from data. We know it and we know how to write it. And we know a lot of other things. We built very good systems for many years, right? So what we know should be modeled, we don't know should be learned. But how do we get there? I don't know. But I think this is, and it's probably not a problem that we can solve ourselves, but at least it's a problem we can work a bit on. And we can definitely collaborate with learning people on that. I brought the slide about probabilistic programming again, because I want to draw your attention that probabilistic programming has a bit of that flavor. So if you remember this weight-height correlation model, what it does, it makes assumptions that the correlation is linear, that this is the structure of this model. It just says, I don't know what is the strength of this correlation, right? And how large the variation is and what is the slope and the intercept of the line. So probabilistic programming, that's why it's kind of attractive to many people. Or building Bayesian models has this feature in a very narrow sense, which allows you to model what you know. This is how things depend on each other and what distributions govern them, and leave holes for parameters and learn the parameters with data. This is a special case, but we would like to do it much more widely, right, than in probabilistic programming. Maybe I can inspire you, maybe you have some ideas. I don't think Antonio is hiding here. Antonio has a series of papers on uncertainty in modeling. So this goes in this direction, but I would like much more radical. And not only from Antonio. Much more radical. I don't know. How about learning more than parameters, parts of structures, or I don't know, how learning parts of behaviors, right? We could explore to push the boundary further, much further. Okay, so I'll be closing here. I would conclude that there is a lot of interesting open research problems in modeling still, right? Modeling research is highly relevant for model software development, and thus it is fundable. So let me change the 3 fallacies to 3 realities. Everybody does modeling, everybody should be taught modeling, and modeling is highly relevant. So on these notes and on this Friday talk. Thank you.
Thank you very much, Andrzej, for this sort of move from complete disbelief to, of course, everybody needs to do this. So that's very
This
great.
was kind of in the cards, right?
It came as a total surprise. So we have time for some discussion, and I'm sure you've all been taking careful notes of all the questions you want to ask, all the points you want to raise. So over to you. I see at the back of the room there, I see a hand up.
What I noticed that whenever such a thing happens more from the AI folks side. So because they are very good in integrating their tools, right? So if they want to build a design space exploration tool for neural networks, they put another neural network into the mix, right? They don't build so I don't know what I'm saying with this. But I'm saying it's a good point. That's something we should figure out, because just putting another neural network on a problem typically doesn't solve the problem sufficiently well, especially for issues like safety and requirements. And they do that. They do safety of machine learning is putting a safety machine learning network that monitors safety. How is that helping? So I think it's a very valid point. It's exactly what we should be pushing.
Packages that they have to do this work. This kind of application data not. We need to have some kind of model where we have this very long projects, but still bring AI and models together. So still, I think they're blocking it.
This is growing. It's a valid point. On this call I was ready for in the EU, actually optimizing for energy conservation and computing power was an important component. Fortunately, I have not seen good ideas. So most of the ideas I have seen in proposals was like, yeah, let's find the cheapest neural network by trying to train them all. And we have just expanded, exponentially more energy to figure out which was the most efficient way. So I think, but I think the energy and efficiency in general is going to help the cause of modeling, because it doesn't make sense to brute force everything.
There's a question here as well, I think a little earlier, and then I'll note to you there as well.
You kind of backtrack on the argument, but you basically said along the lines that don't seem to be modeling, which is correctly say that we do model, but we seem to be very good at keeping our models invisible somehow, that the outside world barely perceives of what we're doing, even though it is important. Say correctly that we even have to go through the AI community because they never even know that they exist.
Yes.
As a subcommunity. But this is unique to this particular engineering discipline. This is the point I'm trying to make. I work a lot with other engineering disciplines, and they're very good at having their models visible. They go to mechanical engineers, go to electrical engineers, aeronautic engineers. You don't have to sell them the point to the model. They will look at you like, what are you talking about? My go-to example is building bridges. They've been doing this for millennia. And sure, they've modeled those. Nobody throws stones into the river and throws some wood over it and says, well, maybe it works. Could have happened that way a couple thousand years ago, but you've come to a point where we build them in a disciplined fashion. And the question really is, how can we as a software modeling discipline find out how to make our models to be this obvious to the whole system as all the other disciplines somehow manage. And I think we've failed that part so far. It's an opportunity, not a.
Or maybe we should just work with these other disciplines. Well, like you were doing.
I mean, we do, yeah. We need to.
I mean, okay, this is a point I removed from my talk because I don't want to offend people. But maybe, what model-driven engineering community has excelled with is actually to eat our own dog food. So we spend a lot of effort in inventing model-driven tools for model-driven engineering. Starting with parsing, graphical syntax, and transformations, interpreters, and debuggers was an excellent one. Right? But sort of first, I mean, it's of course important to eat your own dog food, and this is a domain we know, so we develop very good tools for it. But in the end, it also has this side effect that nobody sees what we are doing because we are the only people who can appreciate it, right? And if you go to bridge building people, you have a much better sense.
I think it's Shakespeare already talks about models for building houses. So there's a question there, I think.
So I think that things like the kind of work I do, even the way modeling, I've been for secondary DSMs for modeling AI machine learning model being embedded within the decision support. It's not AI based, so I've got AI models that are driven by the data that's true. So I think both kind of things provide the modeling, then that's not being extolled in the way that it needs to be. I think really areas like our base scenarios.
I have the feeling that you want to write on that comment. Yeah. So I'm going to stop Andrzej from responding.
No, I want to respond
to the group. Then one moment.
I agree with you.
Okay, yeah, I was going to say this in the second. I think using VR is not for ourselves. So what I was going to suggest is what if we have a personal conferences and then have this personal paper exercises, go out, get a paper in another conference, not related to this. These papers can be presented at models conference or the IP's perfect conference. And would be very, say, okay, you've got a paper accepted in a conference, which is not related to that, it's not modeling. That would be
Many conferences don't do that, right?
That could be another measure. How is our current impact in the society? Are we able to publish papers in conference which are not about models? Absolutely agree.
I'll actually take some chairs for a and ask a question that let's maybe push back a little bit against what you said. So the statement that everybody does modeling, is that just another way of saying, I think it was Nara who said that programming is theory building. Is that just another way of saying that as we build programs, we build abstractions unnecessarily, and therefore we're all modeling?
Well, I think it's more saying that I think this is also quote from not a Turing Award winner, but Marcus Stutter. That there is no difference between programming and modeling. The distinctions are necessary. So basically, people still build systems. They build a lot of systems, and a lot of what they are doing today is what we would call modeling 20 years ago. They just don't call it this. So I think you're not right. I think that modeling doesn't have to be theoretical, even though it, but they have a nation to do things that are formal. I don't think modeling has to be.
And that's not what I meant. I mean, in the sense of that, as we build programs, we always build a theory of the domain.
Yeah.
By creating abstractions, creating classes, creating functions, or whatever our programming language or tool of choice are. And so I guess the more serious part of the question is, what are our sort of unique selling point contributions that we do in Antonio's sense, sell to the world outside of the narrow modeling community? If it's not the specific tools, right? If it's not Eclipse and Ecore and EMF, if everybody does modeling somehow, what is it that we sort of really bring to the table that we go, this is the thing that nobody else can do but we?
Yes, I should correct my statement. I think you made me understood that the statement is a bit too general. I think it would be stronger if we said everybody that's domain specific, because that was mainly what I was trying to go after, to make it more, because modeling in general is also a relationship. Domain analysis, which is very broad in there. Everybody writing a class in principle, that stuff. But everybody seems to be doing domain specific modeling in domain specific languages. Maybe that's should be my point. Now, what was the other thing I want to say? Okay, I don't have a pushback to your pushback because part of my disillusion is still there, and I don't know how to say it politely, but when I sit in ECMFA sessions, there are amazing talks about tools people are building, and I'm technically impressed. But I'm also not doing this kind of work anymore. I would rather go to big robots and have a model with them. I don't know. I have lost, not belief, but I have lost vision for what kind of generic tools I should be building. I did that. That's true. So I haven't built generic tools for some time. That was probably the last one. Yes. That doesn't, I'm not trying to say that one shouldn't, I'm just saying, I don't know. Things became a little too domain specific at some point.
Yes, without wonder, so answer question of code versus or that example that you have shown about this. Remember this use of an API to build a behavior tree.
Yes.
Was so messy. Probably if these people have followed some basic software language engineering principles, they have been like a kind of internal ESL and have thought about the abstract syntax and probably use some operator overloading in Python to make it easier to use.
But also put the model in a separate file and
So some kind of thing. This kind of thing. So this so probably what you are saying is that
maybe we shouldn't focus on doing these very generic tools, but trying to bring this principle to other people so that they can even manually build better domain-specific tools in these Python environments. That's focus so much on doing something that solves everything, and it's better to just do it manually, but no.
It's essentially everyone does modeling, but not everyone does modeling.
Yeah. Yeah, I have some good points here how to revise my slides.
Any other questions or comments for Andrzej?
Basically, to have a session like every intelligence, I guess, in order to, I think something like that in a conference which is more like learning oriented, machine learning oriented, would maybe drive learning community modeling. Because again, MD intelligence, there will be majority of people who are from MD and using learning system. I just feel like having a workshop or something special edition in.
I think that's a good idea. It's difficult. One has to find some people who are already in this community. Otherwise, you'll be just located with no interaction. But yeah, if you know people, so I know the robotics modeling community. I don't know the machine learning people who are interested. I mean, to know that would be very useful to exploit that to create a meeting on these venues.
The discussions will carry on the coffee break as well. It's perhaps let's perhaps first thank. Yeah. In a moment, Vadim's sort of already keen to say something, but before we do that, let's first thank Andrzej again. No, thank you for. Before I let you go, Vadim has stuff to tell us, and let me see, Vadim, whether I can move this window out of the way so we can actually see you. That would be, yes, exactly. Look at this. Over to you, Vadim.
Thank you very much. Greetings, humans. So my name is Vadim, and I have a dangerous role of standing between you and the morning coffee. I work at the University of Twente, and that's where the next stuff will take place in 2024. So if you have been to the website of Stuff 2023, you might have noticed on the menu on the right that it's a part of the series. We all knew that, but now Conf Researcher also does. So that's the most important part at the moment. There is a website, it contains some information. The information will grow over time. Now you also know the location. So Twente is in Enschede. Might not tell you much, but it's in the Netherlands, and it's in the east part of the Netherlands, close to Germany. So Netherlands, Germany, somewhere there. If you know where Amsterdam is, that helps. It's about 2 hours on a train from there. It's highly reachable from Germany as well. The exact dates will be decided very soon, will appear on this website that you now know how to reach. And they will be very much similar to what we have this year. So somewhere around the middle of July 2024. That means that the main deadlines will be around February-ish, March-ish, December for the two-round setups, and around May for workshops. So if you, even after Andrzej's keynote, you're still interested in doing some kind of modeling, then you're welcome to start working now on your ECMFA papers for the next year. If Adrian Rüttel and Judith Michael are somewhere in a room, then you can, in the audience, you can ask them how much of machine learning they are willing to see as a part of the models. But that's the ECMFA part. If graphs are your thing, then obviously ICGT is the venue to be for you, and they will also be a part of the top next year. Around the end of the year, maybe in January, we will finalize the collocated venues, so there will be more workshops and maybe some other things for you to entertain yourself with. That is pretty much my entire announcement. So remember, this stuff was great, but the stuff next year will also happen and will also be a success. And you can start working towards that by thinking what kind of ideas you can put in the papers for the next time. If you have any questions, find me, Stefan, and most of the people know how to find me. And otherwise, go to the website and go from there. Thank you for your attention, and I hope to see you next year in Twente. Back to you, Stefan.
This morning session of the ECMFA, and I think there's a half-hour coffee break. Having only just arrived, I don't quite know where, but I'm assuming it's back there. And then I think we're back here for the final session of this